Good morning, students. Welcome to another lecture of control systems. And today's class, we are going to see about transfer function using Laplace transform. So, before we define this, let us see what your transfer function is. So, your transfer function is given as the output to the input, or it is the equivalent of the gain of the system. But here we are computing the transfer function in terms of your Laplace transform. So when I take the Laplace transform of your output by input, so if your input is x of t, the Laplace transform of x of t becomes x of s, and your Laplace transform of the output becomes y of s. So seeing from here, you can easily guess what the transfer function is going to be. It's going to be y of s by x of s. So most of the time, the performance of your control system is measured with the help of a transfer function. A transfer function, given a transfer function, you should be able to predict the stability, the performance, the efficiency of your control system. So many parameters can be computed by just given the transfer function of your system. So now in today's class, we are going to find the transfer function for our mechanical system. We have seen in lectures previous to this. So what we will do is we will design or we will draw the differential model of your mechanical system and convert that differential model to a Laplace form, which is given by the formula shown here. So let's do a numerical to get this thing more clear. So the question you see in these types are you have to find or you have to derive the differential equations for a mechanical system and obtain the transfer function after doing so. So how do we do these kind of numericals? How do we go about solving these numericals which require us to find the differential equations and your transfer function? So let me draw the question system here where good. So we have two masses shown here, M1, M, presumably M1 and M2, and then you have they are attached by a spring and a dashboard, and you have an external force of Ft acting on the system, and that is subject to a displacement of x1 and x. So the first thing we are going to do is we are going to isolate your masses M1 and M2, obtain the force equation, and then convert that force equation to your differential representation. So once we have the differential representation, we will see how we solve for transfer function. So taking the Laplace transform of your output by input is going to be here taken. So which is your output side? Your output side is the f of t. So you have to take care to see what comes on the output side here and what comes on the input side. So mostly the force f of t acting on the system is the input because that is the force your system is subject to, and depending on that force you produce certain displacement which is your output. So your force is the input, so which means your Laplace transform of these input and output or the transfer function is going to be x of s upon f of s. So the displacement upon force is the transfer function for most of the mechanical systems which are subject to an external force f of t. Now we will isolating the mass m1, we get the force equation which is given by fm1 plus fb1 plus fk1 plus fb plus fk equal to 0, and the relative displacement with m1 is your k and b, because they are connected between masses m1 and m2, so their relative displacement is going to be x1 minus x2. Or in this case, it's just x1 minus x. So the question says it is just x variable. So you have to go with the variables used in the question. So if it is confusing for you to go with x, you can just replace x is equal to x2 in the beginning of your question, and after you do all the calculation, at the end you replace x2 equal to x back. Got it? So it's up to you how you do this problem, but the steps have to be followed exactly how it is shown here. So now we have our fm1, the differential equation is m1 d square x1, fb1 is b1 dx1 by dt, fk1 is k1 x1. So these are all your non-relative terms, and the equivalent Laplace transform is given by m1 s square, b1 s, and k1 x1 of s. And now for your relative displacements, force Fk and Fb, you have the equivalent Laplace transform as k into x1 of s minus x of s plus b into dx1 minus dexs. Good, so that is going to be your bs into x1 of s minus x of s. That is your transfer function. Now we will write the force equation for mass m1 in terms of your differential equation and your Laplace equation or the Laplace representation. So the differential equation is written first. And now I do the Laplace equivalent of my equation 1, which will be used to compute your transfer function. So once I do the Laplace representation, I am going to group my displacement terms together. I am doing this for all the questions because eventually my transfer function is going to be the displacement upon force. So grouping this will help me to obtain the transfer function much easier. So I am grouping my x1 of s, which is the Laplace representation of displacement x1, and x of s, which is the Laplace representation of your displacement x. So grouping them together, I am going to get two terms which are common to x1 of s and the other terms common to x of s, and that is going to be my equation. Good. Now taking the ratio, I'm getting x1 of s by x of s is given by this. Good, so that is with respect to your mass m1, and I'm having x1 of s by x of s for your mass m1. Now we will move on to our mass m2 and follow the same, obtain the differential representation followed by your Laplace representation, and then group the displacement terms together and see where we end up. Good, so let's do it for mass m2. So I let you predict. So here, what are the relative displacements? We have the same fb and fk, since these are connected between masses m1 and m2. Now you have an external force f of t is also acting on m2, so that comes into this force equation, which means your force equivalent is going to be the sum of all forces, which is equal to the external applied force f of t. So your left hand side or the right hand side is not going to be equal to 0, just like in the previous case for mass m1, since there is an force F of t which is going to be equal to all the forces which are acting on M2. So the relative displacements are for your FB and FK as known, and the displacement order is given by x minus x1 since x is your displacement of mass M2 in question. So in the order of displacement for relative displacement, your first displacement is always going to be the displacement of the mass in question or the isolated mass in question, and in this case that is your M2, and that equivalent displacement is x. So x comes first. So you have x minus x1 is your relative displacement. From that I am writing all the force differential representation as given and its equivalent Laplace representation. Good. So now what we do the same steps. We are gonna sum these to f of t. So the Laplace transform of f of t is going to be just f of s, and this is important because f of s is my denominator in my transfer function. So we have already said my transfer function is going to be equal to x of s by f of s. Good. Now if you ask me a question, can I take my transfer function to be x1 of s upon f of s? Yes, you can. So then it becomes your transfer function is defined with respect to point of reference, which is mass m1. So your transfer function is represented as x1 of s by f of s. So x of s divided by f of s is also your transfer function, but if the point of reference you are taking, that transfer function is at m2. So you can have both these as your transfer function of the system. And in your exams mostly, or in any questions, they usually mention which transfer function needs to be found. And in this question, as it is given that we are required to find x of s by f of s, we are going to do it. So I did not write that in the question because I just wanted to tell you that f of s is my input always. That is not going to change, but my output can be either x1 of s or x of s because both are the displacement due to force f of t. And the question says you need to find x of s by f of s as a transfer function. So we are going to do the same here. So after writing my Laplace representation, I'm grouping my x of s and x1 of s terms, and that is bringing us to this form. And on my right hand side I have f of s. So now how I need to obtain my x of s by f of s, that is my transfer function, right? To get my system transfer function, I need x of s by f of s. In order to do so, what I need to do is I need to replace my x1 of s with equivalent x of s. So I'm going to replace my x1 of s from equation 3. And what was my equation 3? So my equation 3 was something like this. x1 of s upon x of s is equal to bs plus k divided by m1 s square plus b1 plus b into s plus k1 plus k. So that is my equation 3. And now I'm going to use this equation 3 in my equation 4, and then what do I get is now I will be having all the terms which are grouped to my displacement x of s. So this makes it possible to obtain or to calculate the transfer function x of s upon f of s as shown here, because my x1 of s is going to be coming from my equation 3, and that is going to be substituted here, and that means I can take my x of s common, and when I do that I can write my x of s by f of s by bringing that to one side and keeping all the other terms to one side. And that is going to be your transfer function for this question, and that can be further simplified by cross multiplications, taking LCMs, or just simplifying and cancelling common terms on numerators and denominators, but I leave it up to you because this is as good as your final answer. Nice. So this is your transfer function for this mechanical system. Excellent. So the transfer function, it's an S-plane representation. So we will see more on what is this Laplace transform, what is the implication of Laplace transform in terms of the control systems, and how this Laplace transform helps us decide on the stability, on some of the key features that your control systems might have, such as like constructive and destructive behaviors of your control system. So we will be seeing those in detail when we do the time domain analysis of control systems. But for now, we are just finding the transfer function using the output Laplace transform upon input Laplace transform for your system, and that should be good for now. Now we are looking at the mechanical rotational system. So you have a mechanical linear system or your translational system, which we have seen so far, where your displacement is x. But when you're talking about rotational systems, which you are very commonly studying it together with translational systems, you have a rotation to be in angular rotation or your circular rotation, right? So that is your rotational system. So when your angle is from 0 to 360, that is your movement of a mechanical rotational system. And this is very common with all these motors which are having RPMs, rotations per minute, right? So what we need to learn is now how do we solve the same differential representation and the Laplace representation and your transfer function for a mechanical rotational system. So what is the substitution? So how does a mechanical translation system compares to your mechanical rotational system? Your force is represented by torque, your mass is represented by moment of inertia, your spring and dashports are the same, but they're called as the rotational dashports and rotational spring, and your displacement x becomes your angular displacement theta. So now that is pretty much it. So that is the same. The rest of the things are the same. The rule sets that we have followed in your mechanical translation system, the same rule set applies to this mechanical rotational systems also. So you don't have to do, you don't have to take much strain in learning these mechanical rotational systems. So let us see how these behave and how we can compute your transfer function. So we'll do so by taking a numerical example for your mechanical rotational system and do the same steps which we have done using the same rule sets. So that is what I have written here. So it follows the same rule sets that we have used in your mechanical translational systems. The questions also look similar. Write the differential equation and obtain your transfer function. So let's do that. So this is my question. So I have my mass equivalents as J1 and J2, and my external force is your torque T, and your relative displacements or your just angular displacements are theta1 and theta. Then I have a spring, rotational spring coefficient and a rotational dashport B. So the same steps we are going to do in order to find the transfer function of this system. In question, they have asked us to find theta of S divided by T of S. So that is given in the question. So your transfer function can be either theta 1S upon T of S or theta of S upon T of S. As it is given, we need to find theta of S upon T of S. We are going to find, so here, so I am going to isolate my J1. So what I'm going to do, isolate J1, J2, obtain the torque equations, and then write the differential representation, convert them to Laplace representation, group the terms of theta 1 and theta of S, and finally we can take the transfer function ratio. Good. So we are going to follow the same steps. The torques acting on J1 are Tj1, Tk, and T. So my total equation is equal to T is equal to Tk plus Tj1, and your angular displacement, relative angular displacement exists for Tk because the the spring is connected between J1 and J2, so the relative angular displacement is going to be what, theta 1 minus theta, because we are taking the moment of inertia J1 is in question. So pretty much the same thing, so we are just doing exactly the same steps which we have done previously but with different notation. So here it is like P, J, K, B, theta. So there it was what? F, M, B, K, X. So there is only this change of variable and rest of the things are the same. Even the Laplace representation for this is gonna be what? J1 S square theta 1s plus K into theta 1s minus theta of s. That is also just substitution of variable. There is not much variation or change in the Laplace representation in your rotational systems. Now we will group the terms. The next step we are going to do is we are going to group theta 1 of s and theta of s together so that we can take this and substitute it to compute the transfer function. So we will be getting two equations for two masses or two inertia blocks J1 and J2, and we are going to take one of those equations and substitute in the other to get the transfer function of the entire system. So if we are doing that, because that means we are taking both the masses or both the inertias in consideration when computing the transfer function, and your transfer function obtained represents the transfer function of the system as a whole. So when I make changes or when I decide on certain things about my system with the help of my transfer function, I am deciding it for the entire system and not with respect to either J1 or J2. So that is what these substitutions or of equations mean. So now the equation 3 is given in terms of theta 1 of s and theta of s grouping. Now I am taking the moment of inertia block J2. I am doing the same here. Again, my K is the common term, but my relative angular displacement is going to be theta minus theta 1 because theta is the angular displacement of the inertia in question. So writing the differential expression and your Laplace representation, I am going to get something like this. Sum of all the forces equal to torque is equal to 0, and that is going to give me something like this. Tj2 plus Tk plus Tb equal to 0, and obtaining the differential form, then writing your Laplace representation, I have something like this. So what do I do after my 4 or after the Laplace representation of 4? I group my terms to be equal to, right, grouping theta of s and theta 1 of s. I'm going to get terms in this manner. So now my transfer function has to be what? Theta of s divided by t of s. So in order to find that, what do we need to do? So let that be my equation 6. So I have my 3 and I have my 6. So I need to club these two equations. I need to merge two these equations by bringing that equation into this or this equation into that. So here what I'm going to do is I am going to, so I'll just writing here what is the Laplace transform of the output by input, and in your question it is given as theta of s by t of s. So it makes sense to bring my 6 into 3. So here I am taking the 6. I can do it either way. So whatever is the best possible way. So if you want to get, always I do it in this manner. So I substitute always in the expression with my f of s or t of s. So here my f of s or the t of s is in equation 3. So I am going to make the substitution in equation 3. Sometimes you may have the t of s or f of s in equation 6. In that case, I do the substitution in equation 6. Good. So hope it's not too difficult to follow. It is something you can just by seeing the equations, you need to decide where you will substitute. You will either do from 1 to 2 or from 2 to 1. Here we are doing from J2 to J1, and in previous question we were doing from M1 to M2. So it can happen both ways. And now you're substituting 6 and 3, and when you do that, you will end up getting your theta of S group and your T of S group. And now you can obtain, or you can write the transfer function as theta of S upon T of S, which will be those terms. You can bring your theta of S and T of S to one side, and whatever terms are left on the other side is your transfer function of the system. Good. So that is how you do these questions. So now I am just writing here, if the question says you need to find theta 1s upon T of S, then you can also do the same thing. You need to substitute theta of S from 6 and 3. So the question can ask for the transfer function in terms of theta 1 of S or theta of S. It doesn't matter, because in both the cases you're going to take do the same substitutions, but except the variables are going to be theta 1s and theta of S. So now we will close this class with a small descriptive statements on force to electrical analogy. So when I'm taking force to electrical, I'm meaning like a mechanical system to an electrical system. And in this we have two categories, which is the force to voltage and force to current. And what do these mean? So what do you need for these systems? So it's very simple. So I have an aircraft where I just I have an voltmeter in my control panel, and by tuning the voltage, I make my aircraft flaps move up and down. Now this is your mechanical to electrical. So how much voltage is required to turn that mechanical flap by so much amount? How do we do that calculation? So in order to understand a mechanical to electrical and an electrical to mechanical control system, you need to obtain this analogous circuits. You need to obtain some analogy which represents the equivalent of mechanical systems in electrical form and vice versa. Good. So here we are only seeing the mechanical to electrical, but we also have electrical to mechanical, which we are not going to be discussing here. So the mechanical to electrical analogy is given for the force to voltage. You are representing it as FMVK, which is your force, mass, dashpot and spring, is given by VR 1 by L and 1 by C. Good. And similarly we have for your force current, we are going to represent your FMBK. So that is your force, mass, dashpot and spring, and that equivalent is given by IC 1 by R and 1 by L. Good. So now this is your force current equivalent, and your displacement X in your current equation is represented by flux phi. Okay, good. So knowing this is important, because if you're taking the force voltage, I'm going to write it. If you find it hard to remember, you can say like my force voltage conversion is LR 1 by C. That is, L represents your inductance, resistance and capacitance. So you reverse the order and take the reciprocal, you get 1 by C RL, right? And then you get it into C 1 by RL, which is your force current equivalent. So you reverse the order and then you take the reciprocal. So you remember one, you can derive the other. So that is the idea of doing this. Good.